So I've been asked to give a tutorial about silicon as a platform for quantum computing. So what I thought I'd do is I've structured it in a way that there is a real tutorial, almost, undergraduate semiconductor physics mini class on the left-hand side. So I'm going to talk about what kind of systems you can use to host spin qubits and what are the, especially for the people who don't work in silicon qubits, you will hear talking about, valid degeneracy, effective mass, and isotopes, and those terms may not mean very much to you. So I really want to show what they mean and how they matter in the way we actually build the quantum computers. And then, having made the decision that we're making spin qubits in silicon, I will do a bit of a taxonomy of the spin qubits, the different pros and cons of various implementations, and then talk about dopants, silicon-silicon germanium dots, and MOS dots. And then Michelle asked me to give a somewhat broader view of what's going on around the world, so where we stand as a center on the international scheme. So I'll give a couple of international highlights. It's a very, very exciting time to be in silicon qubits, and a couple of CQC2T highlights from last year. And then, this sounds like a long list, but I will go quickly through them. All the companies that are currently active and are coming into the field of actually developing commercially silicon quantum technologies. So first of all, host for spin qubits. So a qubit is a quantum mechanical two-level system that must have a number of properties. It needs to have two well-defined states, and you need to be able to create an arbitrary quantum superposition. So you need to be able to define a Bloch sphere and do, let's say, SU2 operations on that Bloch sphere. You gotta be able to initialize and read out in single shot the system, and you need to be able to find some ways to make the qubits interact in a way that appears scalable. Otherwise, you get what's remember, John Martini is calling it the neutrino qubit. It's like infinite coherence, but you don't couple it to anything. So, that's not a qubit, right? All right, so if you look at the books, the quantum information books, they will often draw this Bloch sphere, which when you look at it, just looks like what you would describe, what you would use to describe a spin 1/2 pointing somewhere in space. So in fact, a spin 1/2 system is probably the most natural, the most intuitively simple qubit you can think of. So how about you actually use a spin 1/2 to encode quantum information? For example, the spin 1/2 of an electron. So to do that, you need to hold that electron somewhere. And what you will probably do, you will hold it in a semiconductor. And so you'll be looking at the, say, top right-hand side of the periodic table. And so you'll have to sort of navigate this environment and decide where you sit in there. So I'm going to start with a little chronology. In fact, the first, to my knowledge, single electron spin qubit demonstration was in diamond, so carbon. It was the nitrogen vacancy center in diamond in 2004. Shortly followed by, in fact, a two-electron system, but it created a single qubit, a single triple qubit, in gallium arsenide. This was done at Harvard. And then it took several years before we in CQC2T and HRL made qubits in silicon. It was 2012. And then only, was published last month, in Delft, a former CQC2T person, Giordano Scappucci and his team, showed qubits in germanium. See, the 16 years from going from here to there, you may wonder, why? Why is this so much harder than that, or is it? What happens as you try and navigate this space to find a way to hold your spin qubit? What makes it hard? What makes it easy? Okay? So let's look at where we stand. So I'm going to start with the group 4 semiconductors, carbon, silicon, germanium. As you move down the periodic table, a couple of things happen. So the group 4 semiconductors all have a few things in common. They have what's called the valid degeneracy, which I'll talk about in a minute. And they have spinless isotopes. It means there is a large natural abundance of isotopes of group 4 elements that have 0 nuclear spin. As you move down from carbon to silicon to germanium, the band gap gets smaller, the spin-orbit coupling gets stronger, and the effective mass gets smaller. So I won't have time much to talk about spin-orbit coupling, but think of it as a way in which the spin degree of freedom couples to the orbital and therefore charge degree of freedom, and it has the problem of giving a shorter relaxation time. It gives an easy, quick path for energy to relax to the crystal. But it also gives you the possibility to do fast electrical manipulations, which is actually an interesting feature that, for example, in germanium is being used right now. So let's get to the band gap. Oh yeah, and then as you move sideways, so you go to 3,5 semiconductors like gallium arsenide, you lose the Valley degeneracy, so that's a good thing, but you no longer have spinless isotopes. Okay? So now let me define exactly what this means for the people who are not used to the terminology. So this is sort of electrical engineering version of a band diagram. So, but I actually really like explaining it this way, and I teach it in electrical engineering this way. So imagine you have, I don't know, silicon, for example. So you get a silicon atom in empty interstellar space all there by itself. It's got 2 electrons in a 3s orbital and 2 electrons in a 3p orbital. And then imagine you have many of them and you put them closer and closer together. So this thought experiment where you create a crystal where you can decide the lattice constant. As they come closer and closer together, the s and the p orbitals will start to hybridize. And so you end up with the sp3 orbital, you may remember from chemistry. And eventually, at the lattice constant, that is the real lattice constant for the stable crystal of silicon, you have 4 electrons in orbitals that come from the, essentially from the p ones. There's the valence band, and then there is a band gap to some empty band of states that have an S-like nature. And as you make the lattice constant smaller and smaller, that band gap gets bigger. So on this diagram, you see diamond is here, and it's got a huge band gap. It's 5.5 electron volts, milli-electron volts, sorry. There should be an M. There's something missing here. Oh, electron volts, sorry, electron volts, yeah, right. And silicon is 1.1, right? And germanium is even smaller. Now, this is really the electrical engineering version of a band diagram. You have to look a bit more carefully when you consider an electron, quote unquote, moving through a crystal. Its energy will depend on its momentum. And so in a semiconductor like gallium arsenide, you have what's called a direct band gap. So the minimum band gap is at k equals 0, so when the electron has 0 crystal momentum. In a group 4 semiconductor like silicon, that is not the case. The lowest energy in the valence band is at a non-zero momentum, in fact, a very large momentum. It's 85% of the Brillouin zone. So you need something that has phase oscillations on a scale that is almost the scale of the lattice constant. And because of the symmetry of the crystal, you have 6 degenerate conduction band minima at plus and minus x, plus and minus y, and plus and minus z. And so depending on the confinement, if you want to make a bound state of an electron in silicon, you will have to create it out of suitable combinations of these band minima. Now, this is something that always creates a lot of consternation amongst students who enter the silicon field for the first time. They find it hard to bend their way around what does actually mean to have this value and so on. So let's take it, really from the first year quantum mechanics, okay? Without knowing, you've always seen values your whole life. Take the particle in a box. So that you know how to solve that. You find the eigenmomenta, so that the wave numbers that give you the quantization conditions so that the wave function on the walls goes to 0. And from those, you derive the energies that correspond to those particle in a box quantized states. And so the eigenfunctions will be of the form sine of knx, which when you expand with Euler's formula is some, in this case it's an antisymmetric combination, so it's e to the plus kx plus e to the minus kx, with k has this index n. There's an OI, sorry, yes, typo. Yeah, there's an iknx and minus iknx, okay? So there's basically 2 counter-propagating waves that interfere. Now, what would be a particle in a silicon box? the particle in a silicon box needs to have, in addition to the wave number created by the confinement if you actually make a silicon box, there will also be this extra wave number that comes from the fact that you have to derive those wave functions from wave vectors at the band minima. So that means that there is this envelope that's the same like the particle in a box, and then there's all these oscillations in there. Okay? So when you hear us talking and worrying about valley splitting, what does that mean? So in the particle in a box, you only ever see the sinusoid solution, right? Because the wave has to go to 0 at the walls because the walls are infinite. But in fact, there is also a cosine solution, which doesn't exist in the particle in a box. It will be up at infinite energy. So in general, you have the symmetric and the antisymmetric combination that you can make. And so when you have fast oscillations like this symmetric and antisymmetric combination actually can have very low amplitude at the walls. The walls are never truly infinite in the real world. And so you will find that the symmetric and antisymmetric combination have an energy gap that depends on the details of the confinement. So when you confine an electron to be used as a qubit in silicon, you want it to be in a well-defined valley state. The other valley state acts as a leakage state. It's a state that has a different nature, a different symmetry from the one you're dealing with, and it would give you errors if it became populated. So really the goal of making qubits in silicon is to have a well-defined electronic ground state that is well separated from the other states, and the nearest one is usually something that comes from this other symmetry of the valley combinations. Okay. Now, effective mass, again, this is basic band structure. So if you look at the bottom of the conduction band and you say, okay, now I want to describe an electron wave packet that moves across the crystal, it will have an energy, which is the energy of the bottom of the band, plus h bar square k square over 2m star, where m star is the effective mass of the electron. It's not just the electron mass, and it's essentially the inverse of the curvature of the band. Okay? So that is the thing that becomes smaller and smaller as you go down the periodic table. So gallium arsenide has a very small effective mass. You see, it's just 6.7% of the actual mass of a free electron. In silicon, it's more complicated because you have this valley, so the effective mass is anisotropic depending how you move with respect to this valley minima, but the average effective mass is about half the electron mass. Now, why does it matter? So another first-year quantum mechanics example, the hydrogen atom that you've all seen. So there you know how to derive all the S, P, D, F states. There's a very principal quantum number, then the angular quantum number. And you would have learned about this quantity that's essentially a ratio of fundamental constants of nature is the Bohr radius, 4 pi epsilon naught h bar squared divided by m q squared, which broadly approximately represents the radius of the 1s wave function of hydrogen. You see that in the denominator there is the mass. So now imagine you could make a hydrogen atom in silicon, like I gave you the example of the silicon box. Now imagine the hydrogen atom in silicon. What would that do? So it turns out you can make a very good equivalent of the hydrogen atom in silicon by taking a group 5 donor. So if you replace an atom of silicon in the silicon lattice with an atom, for example, of phosphorus, phosphorus has one extra positive charge, which is not compensated by all the bonds that it makes with the silicon atoms in the vicinity. And so that extra positive charge will bind an electron, just like a proton binds an electron in the hydrogen atom. In fact, it turns out phosphorus also has a nuclear spin 1/2, so it really is, in many ways, the analog of a hydrogen atom. Except it's not a hydrogen atom in vacuum, it's in a semiconductor, in particular in silicon. So what happens then? Well, first of all, the Bohr radius will change. Okay? The dielectric constant of silicon is nearly 12, so that will go there in the numerator. And the effective mass is half the electron effective mass. So approximately the Bohr radius of this hydrogen atom, so the phosphorus atom in silicon, is about 2 nanometers or 20 angstroms. So it's bigger. But not only that, because remember, we have the valleys. So this electron wave function has to be composed from the 6 conduction band minima of silicon. So in addition to being a bigger Bohr radius, it will also have oscillations like this. So that's what the 1s wave function orbital of phosphorescent silicon looks like. It's big, and it's got these tiny oscillations, essentially at the atomic scale. Okay, so now I'm going to pick on some optics person, see if they paid attention. I'm going to pick on Tim. You're right here at the front. Okay. What would a hydrogen atom in gallium arsenide look like, from what I told you? The effective mass is smaller. Yeah. Bigger, yes. And? Exactly, good, Tim, excellent. No, it's a good sign. Exactly right. So in gallium arsenide, the effective mass is even smaller. The dielectric constant is about the same. Effective mass is even smaller, so it goes in the denominator. The Bohr radius will be even bigger. But there is no valley degeneracy, so there will be no oscillations there. So a big, soft, smooth wave function. Now, why do I tell you all this? This sounds like, first year quantum mechanics, but when you go in the lab and actually make qubits in these materials, all these things make the difference between having a cruisy PhD and having a real headache. Okay? Yes?
I don't agree with the answer, because you saw the block function.
Yeah.
So it's at a slightly smaller scale, there's all this fine structure again.
Of course, at the small stuff, yeah.
But not much smaller.
You mean the...
Much smaller than the valley scale structure that you just showed.
Well, it depends how fast, how far from the bottom of the band you go, right? How you confine.
No. We're just talking about the inside the unit cell variation
Yeah.
of the charge density.
Right, yeah.
So it's a fiction to call that smooth also.
Yeah.
And you learn that in hyperfine physics.
Right. Okay. Fine. I was giving a pedagogical introduction, but thank you, yeah. Sometimes you have to simplify to get the message across. All right, so let's say now you want to confine, for example, here 2 electrons in a semiconductor like silicon using electrostatic gates, okay? So this is an example of the device that was demonstrated in 2012. This was the first quantum dot qubit in silicon. So that's, nice device. This is a similar device from the same area. This is from the Jacobi group in gallium arsenide. You see the gate layout is actually very similar. The scale is not. So this one is bigger. And in fact, I think this is not a fair comparison, because I think if you really looked at how big are the dots, the electron wave functions here and there, there's probably at least a factor 3 or 4 in the size of the wave functions. So what it means, broadly speaking, is the following. The lower the effective mass, the larger the wave function, and the easier the fabrication. You don't need to squeeze those gates that hard. You don't need to work that hard to find some electrode that you fabricated in the clean room with all the problems that go on in the clean room to control that device right there, okay? So this is something also Klaus Enslin was mentioning yesterday. Like gallium arsenide is a very appealing material for doing basic semiconductor quantum science, because fabrication is among the easiest you can get in this kind of discipline. But, there's a but. There's the isotopic composition. So now you put an electron in, this is kind of meant to represent silicon, which has a natural abundance of 4.7% of isotope that carry a spin 1/2. And so these nuclear spins, they provide a semi-classically thinking magnetic field to the electron spin, which therefore randomizes its instantaneous precession frequency. So this is a form of decoherence. Now, in silicon, as I said, 4.7% of the isotopes has a spin 1/2, but 92% has a spin 0, and there's another 3% of silicon-30 that also spin 0. There is a whole worldwide effort to purify just the silicon-28 isotope that has 0 nuclear spin. So this is the extreme case that comes from the Avogadro project, where people are looking at creating a perfect sphere of isotopically pure silicon-28 to redefine the kilogram. But there's also more sort of practical forms in which these materials come about, and that's what myself and Andrew Zurak have been using for the last 7 years from our collaborator Koito in Japan. These are silicon epi layers. So it's a normal silicon wafer that has about a micron thick isotopically enriched silicon-28 epi layer onto which we can fabricate all of our devices. So that really makes quite a difference. This is a Rabi oscillation of the electron of a phosphorus donor in one of these isotopically enriched epi layers. So it's a perfect sinusoid that goes on for many microseconds. This is the same experiment done in natural silicon. Okay? It's day and night. This is the difference between having an easy day and a hero experiment. This experiment barely worked. It was the first qubit in silicon, but it was a hero experiment. This one is not a hero experiment. It's actually easy. Okay? So all of the above is really the, let's call it, physics aspect of things, right? And this is what makes academics pick their choice. You know, I want to do this versus that, and there's all good reasons to choose one over the other. I think that the conversation becomes a little different once we include technology. Because if you want to say, okay, I am doing this for the purpose of one day building something, producing something, it's hard to go past the fact that there is a $1 trillion industry whose job it is to miniaturize silicon electronic devices. Okay? So this is really an important factor when it comes to, you know, investment and commercialization. So let's say we've made up our mind and we want to make spin qubits in silicon, okay? So this is an image from a review that many of us in the room wrote a couple of years ago with Floris Vandenberg, who was my postdoc at the time. There's many ways to confine an electron in silicon. I will focus on 3 in particular that are really the most used. One is dopant atoms. Okay, so again, we've chosen silicon and then we move away from silicon on the periodic table. Here we have acceptors, and Sven's group is doing some interesting work on acceptor qubits. And then we have the donors, that's phosphorus, arsenic, antimony, and bismuth. They all have similar properties. The nuclear spin gets bigger and bigger as you go down, so there's some interesting physics you can do with that. I just want to mention briefly double donors. A former postdoc of mine and former CQC2T person, Stephanie Simmons, who's now in Canada, is doing some interesting work on selenium, which has some interesting optical properties. And then if you go down at the bottom of the periodic table, you get erbium, some in the rare earths line. And again, Sven is doing work on this. Erbium being, I don't know if you can call it a donor. It's not really substitutional. It doesn't really care about the silicon band structure. And for that reason, it has a much easier photon emission into the telecom range, in fact. And then you can make artificial atoms, and there's broadly 2 ways to do it. One is with metal oxide semiconductor methods. So you take a piece of silicon, you grow an oxide, typically silicon oxide, and you put a metal at the top. You can pull an electron against that oxide. Or you can make a heterox structure, which is very reminiscent of what has been done in gallium arsenide for many, many years. You have a silicon germanium handle, you have a silicon well, and then silicon germanium cap. This bends the band structure in such a way that you easily confine electrons at this smooth hetero interface. So why would you choose one or the other? So the dopant atoms, here I'm just putting phosphorus is the most common one, have a well-defined confinements, right? They're atoms, they're always the same. They have a huge Valley splittings, that's 10 milli-electron volts. And they have the nuclear spin as a resource that you can use, and my group has done a lot of fun with that. The minus side is that these are really atoms, so they're atomic scale objects, so the fabrication is very hard. And so engineering their properties is not as easy as it is in an engineered structure. With MOS dots, the appealing part of this is that even in a university environment, you do fabrication that is in the broad spirit of what is done commercially in the foundries, in the industry. Plus, from a physics point of view, these devices typically have a very large Valley splitting of order 1 milli-electron volts, which is completely safe. Minus side is also here, the fab is not easy for a university lab. We do it, of course, in our labs, but not many other groups at the university level manage to do this successfully. And the quality of the silicon-silicon oxide interface is crucial. It's really a delicate point of the device. Silicon germanium has a relatively easy fab. A lot of people have moved from gallium arsenide to silicon germanium smoothly because it's kind of the same thing. You just have to make the gates a little smaller. The wave functions tend to be a little bit less tightly confined, which means it's easier to control various tunnel rates and various parameters. The real Achilles heel of this technology is that the valley splitting is small-ish and very variable. I mean, if you scan the literature, you can see some beautiful double quantum dots, and you wonder, why isn't there a qubit there? Well, because the valley splitting was near zero. Okay. All right, so here is a little, I'm conscious of time, so there's a little passage of dopant-based devices. So there's 3 types really that have been developed. These are the top-down ion-implanted MOS devices. So these are really like, there's a large silicon MOS quantum dot, and next to it we implant phosphorus donors. So these were the ones where we had the first single-shot readout, electron spin qubit, nuclear qubit, and a number of milestones ever since. Then there is the bottom-up technology, of course, that's been pioneered and developed by Michel. These are devices fabricated essentially at the atomic level with scanning tunneling microscopes of very high precision in the placement. They had the first single atom transistor in 2012, atomic wires, and then last year was a very good year, atomic 3D fabrication and the swap oscillations of 2 spins. And then there's another technology that Sven has been working on for a long time, also, in fact, before he joined CQC2T, which is to have sort of commercial foundry-based silicon transistors with dopants in there. So Sven has done some really interesting work on single donor transport, Kondo effect, and then since he moved to CQC2T, he had this really interesting result on an erbium atom inside one of these transistors being optically addressed. So this is all really center. There are a few other groups in the world that work in this arena, but I can say with full confidence we are the leaders in the world on this. The MOS quantum dots, so these are single dot. The first single electron dot was made in 2009. This is all done in Andrew Zura's group. Single electron qubit 2014, 99.96% fidelity 2018, and this year 1 Kelvin operation. This is an important milestone. With double quantum dots, 2 qubit logic gate in 2015, and very high gate fidelity of 2 qubit gates 2019. And then again, there are these industry-based devices. These are sort of foundry devices. Mostly I'm showing some Leti devices here made in Grenoble. So here in the corner of this sort of FinFET transistor, you can localize quantum dots that can be manipulated coherently and have some interesting properties. So here, there is a lot more activity, but really the MOS quantum dots work done in Andrew's group in the center really is leading the field. And then there's the silicon germanium. So a lot of the early work was done in Wisconsin in the group of Mark Erickson. And then later on, he started collaborating with van der Sijpen in Delft, and the Tarucha group in Tokyo is now coming on board. So single dots, double dots, and some fantastic results on double dots that I'll talk about in a moment. And then triple dots, which is the chosen pathway of HRL for the purpose of making the exchange-only qubits that David spoke about before. So we don't do that at the center. All right, so now in the few minutes I have left, I want to give a bit of a sense of where are we at in this field, what are the hottest results that are coming on in the international scene. So 2018 was a fantastic year for silicon germanium devices. There were 2 groups, the Delft and Wisconsin group and the Princeton group of Jason Petta, showing 2 qubit logic gates with slightly different implementations. There were both 2 qubit logic gates with electrical control using micromagnets. But in the Delft case, it was a control Z gate, so there was a dynamic control of the exchange interaction. Whereas in the Princeton case, it was fixed exchange interaction, and it was a resonant gate. So they worked in a limit where the detuning between the qubits was bigger than the coupling, and then a pi pulse on one of those resonance gives you a control NOT gate. Then with essentially very similar structures, again, the same groups, Delft and Princeton, showed also in 2018, the magic year, Spin-photon coupling, strong spin-photon coupling in silicon germanium. So in the Delft group, they had this funny shaped resonator and this sort of paddle dots, coupling to a double quantum dot that hosts only one electron. Okay, so you have one electron, two quantum dots. The electron can sort of wobble between the two dots, and there is a micromagnet that couples the charge position to the field that it experienced transversely. So that's how you drive the spin resonance, by moving the charge. And so the resonator vacuum electric field wobbles that electron and couples to the spin degree of freedom. In the Princeton architecture, it's a similar idea in terms of the quantum dots and the micromagnets. The cavity is rather different. These are sort of old school half wavelength cavity, but notice here there are actually two pairs of double dots coupled to the cavity at the opposite ends. Okay? So in this experiment, they managed to show that both the left double dot and the right double dot could be strongly coherently coupled to the photon in the cavity. But that happened, you can't see it here on this scale, but that did not happen simultaneously. So there was one value of magnetic field at which one electron would couple to the photons, and then another slightly but significantly different value of magnetic field where the other electron coupled to the photon. So what they've done this year, I think it was published on Christmas Day, they fixed the problem by changing the angle of these micromagnets at the two ends. So if you design it right, you'll find that there is some value and orientation of the external field at which both spins end up both being in resonance with the cavity. And so in doing this, they could show that there was an increase of the total coupling so that the two spins were coherently coupling via the cavity. This is not yet the demonstration of two qubit logic operations at the distance, but it is the demonstration of the physical link that, with the right energy scales will allow two qubit logic gates of spins that are separated by essentially a centimeter across the cavity. So this is really the state of the art at the moment in this field. CQC2T highlights, I've chosen two from last year, both Nature papers. So this one is from Michel's group. I know you've heard about it many times. So this is a donor dot device. This was, if I remember well, a 2p and a 3p cluster. Is that right? So a cluster of two donors on the left and three donors on the right. And then you work on the unpaired electrons on the outside of it. So there was a lot of work, of course, finding the perfect position for these two dots to have the right value of the exchange interaction in the right range. The exchange interaction was tunable with gates. One important part of the experiment was the independent readout of both spins, so they could read spin the left dot and the right dot. And then to do the coherent exchange operations, so this device didn't have a microwave antenna to actually coherently control the qubits, so there was a loading spin down on one spin and random loading on the other, so half the time you'll get an up-down, and then you can watch those swap coherent oscillations happening, and these are extremely fast oscillations that are on the nanosecond or sub-nanosecond scale. So this is one of the essentially records of speed for exchange oscillations seen coherently. And then another highlight from 2019, this is from Andrew's group. It's from the MOS double quantum dots. So the two qubit logic gates in this kind of dots was already demonstrated in 2015. But by, polishing up and improving the structure, they managed to get the fidelity so high that it was possible to actually run this sort of gold standard of assessing the fidelity of the quantum operations, including of the two qubit logic gates. So by doing this randomized benchmarking of the Clifford gates, they found a fidelity of the native, let's say, C0 gate, C-Rod gate of about 98%, which is essentially the state of the art in silicon at the moment. So finally, a little word about where is this going in terms of commercial engagements. So, as I was mentioning before, you can do the whole physics of things and decide where, as an academic, you want to put your bets. But if you want to actually build a scalable and commercializable quantum computer, you're going to have to start thinking carefully about what opportunities are there and what the industry will want to hear from you. So I'm going to do this in a chronological order. In the last years, I think companies have been popping up more or less at the same time, so don't blame me if one came out 1 month before the other, but I think it's quite certain that the first one to get into the field in the mid-2000s was HRL Laboratories. Okay? So this was the company that really pioneered the accumulation mode silicon-silicon germanium devices, which really made all the fantastic results I've shown to you before on silicon-silicon germanium possible. They are focusing now on the exchange-only 3-spin qubit system that David was talking about before. And I want to mention they have a vast device modeling expertise. So we actually collaborate with them in certain occasions, and this is very, very valuable. They have a massive in-house expertise in this field. And then we have our own Silicon Quantum Computing Proprietary Limited, which is in tight partnership with UNSW. I only just last night looked at the website again, and I discovered there's new things coming up. There is this interesting, really like, you know, milestones roadmap. So 10 qubits by 2023, this is what we knew for a long time. 100 qubits by 2030, and a universal quantum computer by the mid-2030s. There's Michelle, of course, and there's Stephen Menzies, who is the chair of the board. This is, I'm not sure if I would call it a startup. It's some of the biggest corporate players in Australia. There's the Telstra, the Commonwealth Bank, New South Wales government, Australian government, and UNSW. So it is a startup, but it's backed by some very large corporate partners. Then we have well, how can I call it? The big fish in the pond. It's Intel, of course. That is the largest semiconductor company that about 2-3 years ago, so more or less the same time as SQC was started, created a partnership with QuTech in Delft. And so publications are not abundant. Something will come out. For those of us who go to Silicon Quantum Computing conferences, they do present results which are absolutely spectacular. So there's definitely a lot going on there. They provide essentially 300 millimeter wafers with isotopically enriched silicon and all the technology that an Intel foundry is able to provide to you. And they're also working on cryogenic control electronics. So they have a apparently large effort in, again, going back to David's talk, what does it take to put the electronics down in the fridge? Intel is starting to work on that. Then there is the CA-Leti. So this is an initiative in Grenoble in France. It's got government backing. So there's a number of research laboratories here. And then there is Leti, which is essentially a research foundry. So they have similar kinds of facilities you would expect in an Intel foundry, but they do contract research as well. So they're a little more flexible in the way they can, develop their devices. And so they're working at CMOS-based silicon qubits, also germanium-based apparently, and also cryogenic CMOS electronics. Then this is a more recent, I don't know exactly when it started, but I think it's in the last year probably. This is started by John Morton and Simon Benjamin in the UK. I think it's in quite close partnership with UCL, University College London. There isn't much on their website about what exactly they do, but it's silicon CMOS devices essentially. And they also look at broader architectures for scalability. And then this is very, very recent, announced on the 16th of December 2019. Our other guest, special speaker from yesterday, Klaus Senslin, is involved in this. So this is a partnership between another industry giant, IBM, and some of the top universities in Switzerland, so ETH Zurich, where Klaus works, University of Basel, and the École Polytechnique Fédérale de Lausanne. Interestingly, from their website, you see that they have essentially the same milestones and goals as SQC, but they don't say when they're going to hit it. So with this, I'm going to wrap up more or less on time. I just wanted to finish with a slide on the CQC2T way of the future. We've seen some of these pictures being floating this morning already in Lloyd's talk. Essentially, with the 3 ways we have in CQC2T to make qubits, we are looking at large-scale architectures. This is the one with implanted donors. using flip-flop qubits that I haven't had time to talk about, but hopefully you saw Rosti's poster yesterday, or it's still up there. So this is a way to have implanted donor qubits that communicate at about 200 nanometer distance or via microwave cavities. Then we have the MOS quantum dot spin qubits. So here you can really try to take full advantage of the compatibility of this technology with MOS fabrication, and so use the gate pitch and the multi-layer stacks of interconnects to wire up these entire devices. And then there is the STM precision place donor qubits, where you can go in the third dimension, so you can make devices that have precisely placed features, not only in one plane, but in several planes. And so you can have, for example, readout devices where the current goes vertically, and then you have the donors in a square array, and you communicate with them by doing some crisscross control of the control lines. So this is all I had to say. Thank you for your attention.